recall that we have two different unit systems, the US customary system and the SI system, and that each one of those systems has different definitions for what length and mass and force and other properties are. However, when we're working as engineers, we often need to be able to translate back and forth between those two systems in order to communicate with engineers working in a different system, or to make sure that the problems make sense relative to our own mental models. Now, when we do that conversion, fundamentally what we're doing is we're setting up a ratio equal to 1, where a certain number of one unit is equal to a certain number of other units. And we have this wonderful guide in the FE reference handbook that tells us what those conversion factors should be. So for example, if we're thinking of feet, 1 foot, based on our conversion guide, is equal to 0.3048 meters. Likewise, we could say 1 inch is equal to 2.54 centimeters. But more than just having those numbers, we need to have that mental model. So for example, I have a meter stick and I have a ruler, and we can see that roughly speaking, a meter is about 3 feet, which is exactly what we would get there. It's a little more than 3 feet, but it's about the same ratio. Likewise, if we think of an inch versus centimeter, if you have a ruler handy, often they have the centimeter and the inch on the same scale, and you can see how it takes about 2.5 centimeters to equal 1 inch. Another common unit we use in lots of engineering disciplines is force, and so that's thinking about the push or pull on an object. And for those who are in the US, maybe a pound is something you're familiar with. So for example, a standard can of vegetables weighs about a pound. But for many of us, we're not as familiar with what a newton is. So if we look at our conversion factors, we'll see that 1 pound is equal to 4.448 newtons. What this means is that you should go to McDonald's sometime, and instead of ordering a 1/4 pounder with cheese, order a 1 newton with cheese. Because you see there's 4.448 newtons to a pound, so when you take that 1/4 pound of meat, right, there's 4 newtons to a pound, and you cook it down, and that little meat patty weighs 1 newton. So that can be kind of a fun way to do that. Don't do that, they'll spit in your food. It's fine. All right, now, so that gives us a sense of what a pound is about. Now, as a civil engineer, I tend to work at a larger scale, so often I'll use a unit called a kip, or a kilopound, where we combine the kilo prefix, 1,000, from SI, with the US customary definition of pound. Likewise, a newton isn't very big, and so as a structural engineer, I'm often using 1,000 newtons, or a kilonewton. Now, while we're talking about force, it's important to recognize that mass and weight are not the same things. So, for example, you might be tempted to think of a kilogram. So this is a large soup can. It has a mass of around 1 kilogram. However, that is not its weight. Weight is a push or pull. Mass is how much of a thing you have. Those two things are related by using a version of Newton's second law, where we take the mass of the object and we multiply it by the acceleration due to gravity. This gives us the definition of what a unit of force is, the newton, where we have the mass in kilograms and the acceleration in meters per second squared, giving us 1 newton. What this means for us is on Earth, if I have a mass of 1 kilogram, I multiply it by 9.81 meters per second squared, the acceleration due to gravity on the surface of the Earth, and I find that my can of soup weighs around 9.81 or 10 newtons. So you can think about like 2.5 pounds of meat, give or take. So that's kind of a close thing there. But pounds and newtons are equivalent. Kilograms is a mass. And so you'll need to keep this relationship in mind when we get into it. Now, another common unit that we use is that talking about pressure. So when we think about pounds per square foot, we're taking our soup can, our 1 pound, and we're applying it across a pressure of 1 foot squared. So if you think about taking a bathroom tile, or maybe even like a bathroom scale, taking your 1 pound of vegetables, spreading it out, the pressure on the bottom of that pan would be 1 pound per square foot, or PSF. Some of us may be more familiar with PSI, pound per square inch. And when we think about pound per square inch, now you're taking something with a base of 1 inch squared and you're applying the whole pound to it. So this is a much larger force based on having a much smaller area, much larger pressure. Now, a Pascal is an interesting unit because a Pascal takes 1 Newton, and distributes it across a square meter. So remember, our Newton is that quarter pounder meat patty, but a meter squared is pretty big. Think of like a very large card table. So if you take that meat patty and you spread it out over such a large area, it will be very little pressure. So frequently, we think about a kilopascal, or 1,000 newtons per meter squared. Again, just to remind you of some mental models, a soup can, that's your pound, a quarter pounder with cheese, that's a Newton. For what it's worth, I'm a relatively big guy, and my weight works out to about a kilonewton. So I don't go around telling people that all the time, although now it's on the internet. So that gives us a sense of some of the relationships that we might be using. Frequently, we'll have our 2 different ways of defining these things. We'll break them into their component units and then use our factors that are equal to each other to set up ratios equal to 1, multiply whatever our property is, watch the units cancel out, and be left with the same property now described in different units. So let's look at our example problem. All right, let's consider this retaining wall problem. So a retaining wall is typically a concrete face that's used to hold back soil. In this particular problem, we're attempting to calculate how much pressure the soil is applying laterally, so left and right, into the base of the wall. That's this value here on my sketch. Now, our problem statement gives us the equation. It tells us that the unit weight of soil is 125 PCF, that's pounds per cubic foot. So if you took a box 1 foot to a side and you filled up with soil, it would weigh 125 pounds. The height of the wall is 10 feet, and our lateral earth pressure coefficient is equal to 0.3. Ultimately, we're trying to calculate that lateral earth pressure at the base of the wall. However, what's interesting about the problem is that we've been given all of our problem parameters in US customary, but we're being asked for the result in SI. Our procedure is to first sketch the system, which you can see I've already done here. I have my wall, I have the height of 10 feet, and then a distributed load drawn into the wall. My next step is to just calculate the value. So when I look at this situation, I've been given an equation, sigma prime x equal to gamma HKA, where it's one equation with one unknown. So all I need to do is plug in all the values I have. Now, when I do this, I'm an engineer, so I'm not just going to write the numbers. I'm also going to write the units. I'm going to also go ahead and reframe the units so that rather than PCF, I'm going to describe it as pounds per foot cubed. And this lets me do my unit management and my unit conversion a little bit better. So there's my unit weight. My height is 10 feet. My active lateral earth pressure coefficient is 0.3. You'll learn about all that in your geotech class if you study as a civil engineer. Now, when I do the mathematics here, and I use my calculator, I get an answer, a numerical answer of 375, and then we'll want to check our units to make sure that this came out. So one of the feet will cancel, leaving me with pound per feet squared, pound per feet squared, or PSF. If you wanted to, you could convert that to PSI. It works out to about 2.6 PSI, so 375 pounds on a bathroom scale or a kitchen tile. Feels like a fair amount of pressure when we're talking about lateral earth, but that works out to a relatively small PSI because the area is so much smaller. So it doesn't really compare to things like tire pressures. All right, we've got our value calculated, so now we want to do the conversion of that value. And so when we convert that value, sigma prime x, 375 pounds per feet squared. What we want to do now is we want to multiply this by values equal to 1, but that have equivalent units in the top and bottom. So if I'm going to deal with the pound first, I'm going to want to be able to divide out the pound. So I'm going to put it into the bottom. The SI unit is newtons, and we remember that for each newton, we get 4.448 newtons per pound. So we need 4 of those burgers to get our pound of meat. So we got there. Now when we think about feet, I'm going to put feet in the top, and that means we're going to have meters in the bottom. We said that was 0.3048 meters. 48 meters. Now the interesting thing here is we have 2 feet, so feet squared. So I actually need to take this conversion factor and square it. That means I'll get feet squared, which will cancel. I'll get meters squared, and then the 0.3048 also has to be squared. So when I put these values into my calculator, I get a value of 17954. And then if I check my units, my pounds will cancel, and then both of the feet will cancel, and I'll be left with Newton meter squared. Newton meter squared, which we remember is a Pascal. So this is 17954. Pascals. But what we wanted it was in kilopascals, because that's a very large number. And so, if we want the kilo to show up, we'll need to divide the value by 1,000. Again, I'm multiplying by 1. Kilo is 1,000, so K over 1,000 is equal to 1. And when I do this, I'll get a final answer of 17.954 kilopascals. And so, I would then report my answer, probably with 3 sig figs, as 18.0 kilopascals as my pressure at the bottom of the wall. Hopefully that helps. Here's your practice problem. I look forward to seeing you on campus. Take care.